Hello, all. Good evening. Looking forward to an interesting discussion over the next 45 minutes about motion planning in general in autonomous driving. So, first, we will know what is motion planning actually. What are we going to do when we say we are doing motion planning in car, or when you go to a motion planning engineer and ask him, what is your role? What is he going to say? And the second, what we are going to do is where does it fall in different stages of making an autonomous driving car or in a system level ADAS systems. So tackling an autonomous driving car, it's like solving that problem is a very huge problem. That's why we deconstruct into different levels. And there are different SAE standards where they have proposed different set of classifications. But in this talk, we're going to see some of the classifications and some of the layers where our motion planning is going to fall. And next, we are going to go over what do we generally need to know when we say we want to know about motion planning or we want to do the motion planning. What do we generally need to know? What are the mathematical concepts? How do we go about the structure of the problem? So we will discuss about that. Then we will discuss the problems that sparked my excitement to come into motion planning. So I went to my prof in my graduation and I asked him, "So what are the problems that we can tackle?" He said, "We can tackle motion planning, and there are this we are doing in the lab." So then, how did I go about the problem I saw, and how did I solve it? And in the last set, we are going to discuss about how is the field currently autonomous driving in general, and where is it going, and what are the different career options that are there in motion planning and control. What is motion planning? So what does planning motion mean? On a high level, when we say we are doing motion planning, we say that we are moving from a point A to point B. We are making the ego vehicle in our case means the car which we are going to drive on road. Now on a high level, we are trying to move from point A to point B. Now this car is going to have a certain initial conditions, like suppose you're going on a highway at high speed, say 80 kilometer per hour, and you want the autonomous driving system to take over. Now okay, I'm bored of driving at 80 kilometer per hour, and now I want the system to drive by itself. So when the system is receiving the control from the driver, it has certain set of initial conditions. I'm traveling at this velocity, I'm traveling in this direction, I'm traveling with this amount of acceleration. So these initial conditions have to be taken care when we are moving from point A to point B. And at the same time, we have certain constraints that we need the car to follow. Certain constraints in the sense, the model we develop as an engineer, it should not make the car go and hit some person. It should not go and hit another car. It should not travel on the footpath. It should travel on the road. So there are different rules, different set of rules which the car is supposed to follow. How do we mathematically formalize that? How do we make the car do that? Comes under this motion planning while traveling from a start point to an end point. Some of the examples generally we see while doing motion planning is, so how do we plan the car? You see a construction site. How do you go about it? The road is blocked. How do you plan? How do you take a U-turn? How do you take a U-turn in high traffic conditions? So these are all the different set of problems which in general we see when we are developing an ADAS system, or when we are thinking widely about motion planning problems. So what are these levels in this motion planning problem? So whenever we see a huge task at hand, the most efficient way to handle the task is to break it down into different levels, and we go on and tackle each level, which has certain set of abstractions and certain set of the goal points. Like uh, suppose in this motion planning problem, the first is the mission level planner. Mission level planner is a planner that is going to plan in the order of kilometers. Like say you want to go from like the current location unto the Domino's, and you want the car to track that. You want the map of those points, you want the reference points. So that comes under the mission level planner. And in the mission level planner, you have certain set of abstractions. Like while doing that plan, you don't care about whether the pedestrian is coming on the road. You don't care about whether the traffic light is on or off. So that set of problems, you leave it to abstraction. And so that is mission level planner. And how do we go about the mission level planner? There are for example, I'm just giving an example. Some set of algorithms we have is Dijkstra algorithm, A star search algorithms. So these are the algorithms we use to get an initial global reference in the order of kilometers of how do we plan the path. Now the second set is behavior level planner. The behavior level planner is something that is going to go about the local conditions of the road. Suppose you are at the intersection. Where do we stop at the intersection? Do you go and stop in the traffic island, or do you just stop at a stopping distance? Now when you go from a low speed lane to high speed lane, how do you go about it? So that set of local conditions are planned in the behavior level planner. So some of the examples how we tackle this behavior level planner are, some people write finite state machines, some people write rule based systems. The problem with writing finite state machines is, if there are limited number of states, that is fine, that is cool. Yeah, we can write, we have a condition, we have an initial state, we end up at a terminal state, and then we go about different set of, some super states. We have different set of, layers which we can try to handle in state machine. But by each addition of new state, this I have seen practically while working, by each addition of new state, you need to take care of different set of interactions between one state to another state. Now what happens in this particular state, sudden different conditions which is corresponding to another state is going to come. So you need to take care of different set of interactions while you are writing a finite state machine. And the second kind of approach where we tackle this problem is by following a rule-based system. Rule-based system is, you have a certain set of predicates, you see the road, you get an understanding of what is happening on the road, then you have an evaluation module, then you have an implementation module, and finally you come up with set of rules that the ego vehicle, the autonomous system has to follow in a particular situation. And these rule-based systems, as well as the finite state machines, each has its own advantage and each has its own disadvantages. Now coming to a low level planner. Now this is the interesting part I'm telling you. So the low level planner is something where we have certain set of rules laid out for us. We have I know what I have to do in a particular system, and I have certain set of references, like what reference track I need to follow. I have certain set of references which I need to follow, which is coming from the mission level planner. Now what I need to do is I need to take care of the local scenarios that come in my situation. Like, I'm traveling on the road, I'm going to watch a movie, and suddenly some pedestrian comes and he runs across the road. You should not tackle the car. You should not with the car you should not hit the pedestrian. So that typical fine elements you get to control in this low level planner. How do we tackle those scenarios? How do you attribute to the noise in the environment? So that kind of scenarios you generally tackle in the low level planner. And finally, coming into vehicle control. Now this low level planner is going to plan, and it's going to give is going to tell the car, you have to follow this velocity, you have to go at this acceleration, you have to go at this angle. So it is going to tell us different set of values or inputs that the system has to follow. Now in the control layer, what you're going to do is you have to follow, you have to reach that particular set point, whatever the low level planner is giving, we have to follow that set point. So this kind of structure we see is called the hierarchical structure, because the base structure is depending upon the top structure and its inputs. And top structure is considering the base structure as a black box. It's not considering anything coming back. We can model some feedback systems which are interesting, but generally this is a basic structure. This is a hierarchical structure of the motion planning. Now we have understood what we are supposed to do. In general, we have gotten an idea what a motion planning problem is supposed to do. But where are we in general when someone comes and asks, okay, you're trying to make an autonomous driving car, what level do you operate? So we need to have a clear structure in the map. So when someone asks you, you need to know your location in the whole hierarchy of the problem solving for an autonomous driving car or ADAS system. Suppose tomorrow you're working in the company and you have certain problem, you're facing a certain problem. You need to know where you are supposed to go and ask, do you have a problem with the data? Do you have a problem with state estimation? Do you have a problem? Did you see a new safety problem? So you need to stay at a state where you have a global idea of what are the different sets of systems that are working in parallel in order to realize the autonomous driving system. This is the structure, general structure. First is the perception and environment representation. Perception and environment representation, the name itself says that, it generally includes tracking a car's motion, identifying various elements in the world around us, like road surface, road signs, vehicles, pedestrians. You need to identify them. Maybe you need to draw a bounding box, give a coordinate, a Cartesian coordinate, or whatever coordinate system you follow. You need to give the data by observing the environment. And then we come to sensor fusion and state estimation. This is one of the important modules in the hierarchy of the motion planning. Now there are different sensors there, with different levels of precisions and different levels of field of views, you different orientations and different positions. You see a wide range of sensors that are attached to an autonomous driving car. If you are into autonomous driving, you might be knowing the famous discussion that is happening around in the circles, which is, whether to equip the car with a lidar or whether not, whether should we just follow the camera. We have different set of sensors that the ego vehicle has. And now sensors are not perfect. Like suppose you measure a certain quantity at one point of time, say t1, and then you measure the same quantity at same position at t2, you may not receive the exact value. That depends on the amount you spend on the sensor or the quality of sensor you have at your hand. In order to handle that scenario, you have a team or you have an engineer where he performs the sensor fusion and he gives the state, he gives the location of the car in the whole environment, and what are the different states that are happening that the car is seeing. And so that state estimation and the sensor fusion process of eliminating different sets of noise, the Gaussian noise, or different sets of noise you see is happening in this sensor fusion and state estimation module. Like you may hire the world's best control engineer. If he's working on the wrong states, then the whole problem is going to go for a toss. So this is an interesting module, and it's an important module. And then comes system and safety analysis. The system and safety analysis is like, okay, now we have what environment is seeing. Now we have the states. Now we have the location of the car. Now we have a general idea of what is happening in the environment. Now we need to sit and analyze what scenarios that the car can tackle, what it cannot tackle. Suppose you are going on a road and suddenly a tree falls. It's a very drastic scenario. It's very tough to tackle that problem. But how do you take care in that case? How do you, at least even if you go and collide, you need to collide in a safe manner that is not in danger. So you have to plan, you have to lay out certain rules that the ego vehicle has to follow. You have to write a set of requirements. You have to define the operational design domains the ego car is acting under. Big companies spend lots and lots of time in this systems engineering and safety analysis, where they get different set of requirements right, and then they go to different various levels of various rounds of discussion, where they finally come out with a certain set of requirements, and on a piece of paper they have that requirements ready. Okay, now we have to follow this set, and that's how we are going to realize the model. And then comes the motion planning. So we have the data, we have the states. Now in motion planning, and we saw the different layers of hierarchies in motion planning. In the motion planning module is going to tell you how do you achieve the particular state you want to achieve. What are the different velocities? What are the different set of accelerations you need to have? What are the different set of the states that the ego car or should undergo based on the environment, based on the different cases you are asking it to go. And once the motion planning has reached at a specific set point, it's going to give a specific set point velocities or accelerations in. Yeah. Now this is this is a set of hierarchy we see in general in autonomous driving, and where are we operating, at what level are we operating, and what are the different set of inputs we see. So what are the different problems we solve when we say we are doing motion planning? We solve path planning problem, we solve velocity planning problem. We go into higher order variables sometimes. Like suppose this is an example. Suppose you're traveling at 10 meters per second now, and then your motion planner, it says, okay, now in order to avoid the collision, you need to travel at 100 meters per second in 1 second. Okay, from 10 meters you need to jump to 100 meters. but there are certain restrictions on the car. Your car cannot, if you are driving a nano, it cannot within 1 second it cannot pick up that high velocities. So you have a system, constraint. And you have a driver comfort in your purview when you're modeling. Okay, my driver should not face sudden jerks, so should not face sudden shift in acceleration, should not face sudden discontinuity in whatever outputs I get. So you act on different orders of variables so that you ensure that there is a smoothness, there is a continuity in different inputs you have in the system. And one more problem is avoid hitting obstacles. You predict sometimes. We'll be discussing model predictive control, which is an interesting problem. So we predict sometimes, then we follow a certain vehicle, then we change the lane, we take a U-turn, staying in a lane. The problems are unending. You have different set of problems that you can solve in this particular module. Now, how do we solve these problems? So we have, till now we know, okay, we know we have a structure for motion planning, we have a structure for autonomous driving. We have different set of problems. So we saw a different set of problems that we are supposed to see. But can we get a general layout, like on how we solve these problems? This is the layout which I have broadly written. The first is we consider a motion model. When you're considering a motion model, what do I mean by considering a motion model? So I need a model that is going to replicate the behavior of the car. The fidelity of replication, the quality of fidelity, it depends on the different problems I'm tackling. In some cases I might stop at I might stop at kinematics. In some cases I might stop at very basic models. In some cases I might go, I need a deeper level of understanding. I need to go into dynamics. I need to understand the gear ratios. I need to understand the frictions that are acting on the car. So we need a motion model that replicates the different set of behaviors of the autonomous driving car. Yeah. Some examples of the motion model is kinematic modeling. Kinematic model is something where you just consider the geometry. You consider the geometry, like you have the car is going in this direction. The car is going at this velocity. I have this amount of horizontal velocity acting. I have this amount of vertical velocity, the lateral velocity acting on the car. Yeah, sometimes you consider vertical velocities also when you go on an incline, when you go through a speed bump. So you consider all these velocities based on the geometry, basically the geometry. And in some cases there is a dynamic, you need dynamics models. You need to understand the tire forces, you need to understand the tire stiffness, you need to understand the gear ratios, how the torque converter is acting. So you need to understand different set of what different set of processes that are happening in the car. So you have these two different set of models which you kind of pick based on the kind of problem you need to solve, and the quality of output you want. And then we formulate the objective. Then you mathematically formulate the objective of how do I solve this problem. Is it reaching set of waypoints? So how do I write the cost function, and how do I smoothen my angular velocities? You have a set, you formulate an objective, and then you look for the constraints that stop us from achieving the objective. The constraints here, I already told, like you're going on the road and suddenly a pedestrian is going to come. You need to avoid hitting the pedestrian. You need to slow down. Even though, like, while setting the constraints also, you have certain tolerances you act with. Okay, this amount of discomfort I can bear, but it should not be greater than that amount of discomfort. So you have different set of tolerances, and in the constraints sometimes you can model the different set of driving styles. Like, say I'm an altruistic driver, I'm a selfless driver. Okay, I will, when I'm moving on the road, I'm that person who says, oh, hey, your stand is bike stand is open, or someone like, you go forward, I have all the time in the world. I might be that kind of driver, or I might be an aggressive driver where I don't even give any scope for other driver to go. Like, when there is when there is an empty space, I go and put my car, or I go and put my bike. So I might be that aggressive driver. So these are different set of driving styles you observe, and how do you capture those driving styles? And when in different set of opportunities, different set of scenarios, you might need different set of driving styles. So that you kind of put it in the constraints or in the cost function? How do you penalize it? So that comes under the constraints. Then we find the inputs. We have this optimization module or some module. We have this reinforcement learning model or some model, which is going to give us a set of inputs that the car is going to follow. And then we give it to the system and we are happy now. Yeah, we have solved the problem. Is it? Did we? Let's see. Okay, now we have this common objective. Now we have the common objective. Now we know. Okay, generally when you're trying to perform a specific maneuver, you have a set of structure in your mind, what you're going to do. But how different, how varied, there is a wide research that has been going since 1980s on the robotics, the motion planning approaches. A different set of collision cones, the optimizational planners, variational planners, sampling based planners, different set of schemes that are available. But what scheme do you pick for this particular scenario to act? So for that, you need to have a rough idea of over different set of schemes that are available, the different set of motion planning schemes that are available in robotics. Yeah. Usually there are two major classifications. One is traditional approaches. In traditional approaches, there is like fine motion planning, gross motion planning, and then there is a non-traditional scheme. Non-traditional schemes are those soft computing methods. Soft computing methods, I mean the reinforcement learning model, the machine learning model, which you see. You consider the whole car as a black box. You have set of inputs, you give certain set of inputs, and you observe the different set of outputs, and you tend to come up with a policy or come up with an action that maximizes the certain reward. You model the whole model motion planning in like, say, if I'm giving this example in the name of a reinforcement learning problem. Suppose you have the car going in a certain direction, and you want to maximize the reward every time the car is traveling along the center of the road. So you tend to write that reward function, you tend to write that cost function in this reinforcement learning. And finally, the model itself tries to learn by doing many trials. It picks you define an action space, it picks different sets of actions, and then it gives different sets of inputs, and finally the car will learn a policy, where the car itself, you just leave it and the car learns itself on the road. Now this is the non-traditional scheme. But there is a problem with non-traditional scheme. Problem with non-traditional scheme is, if you go with to some machine learning approaches, they are very data hungry. If you go to the model and ask, okay, I have fed you with like 21 terabytes or 30 terabytes of data, but why did you go and hit that person? Then the model simply says, you didn't provide me that data. I just lack that data. So it's data hungry, and you face millions of corner cases which the car cannot notice, and it goes and hits the car. When you go with reinforcement learning based approaches, what happens is, you need to train it for 30 days, 40 days for proper lane keeping behavior in certain highway scenario. So now see that. Now imagine imagine making a model to travel in a basic Indian road where you have animals coming across the road, you have cars, aggressive drivers on the road, you have jaywalkers on the road. Now that is going to take lots and lots of time and very refined policy making. Then we have seen there is a lot of research that is happening in this non-traditional schemes as well. But we are interested in these traditional schemes where we can mathematically model what is happening in the car, what the car is supposed to behave, where we can mathematically model the system, which is purely based on physics. So you can understand when the car brakes, you can understand, okay, this is the reason car has broken, and this is the reason why my car is not acting. It's not relying on the physics where it's supposed to do. So then you model it differently. You have certain sort of, I see certain sort of truth in traditional approaches when I write. I mean, I'm not taking sides, I like both, but still. So I'm going to speak about the traditional analytical approaches in this talk. Yeah, now let's summarize till now what all we have done. So we identified the task we need to do, then we knew about the model of the vehicle. Why do we need to pick a model? We understood the kinematic model or dynamic model in order to achieve this objective. And then we plan this trajectory, then we write a control scheme, we we make use of these PIDs and other advanced techniques, like which is model predictive control, to achieve the specific objective which the car is supposed to achieve. Then we send these controllers to the actuators like throttle, brake, and gear systems, throttle, brake, and gear systems, and we see the ego vehicle performing the task which it is supposed to perform.